right, here we go with 9.1.1 or part one. We're going to split this up into this section into two different lesson videos because it's a very meaty section, as they say. So you can see we're going to learn all the properties of radicals. The nice thing is that you've learned a little bit about radicals already. So and you probably know a fair amount of this, maybe even from pre-algebra. And if not, that's okay, because we're going to do it now. All right, so why don't you go ahead and try and do as many of these warm-ups as you can on your own. Some of them will be very simple, and some of them will be maybe a little bit more challenging. But go ahead and give it a shot. So pause the video and go for it. Okay, I'm back. So obviously this one, hopefully you put 4, this one 8, this one you should know also, because remember we learned them all up to 400, and this one is 15. Now this one gets a little bit more tricky, 2025. So what do you know that, what number times itself will give you a ones digit that ends in a 5? It's only one that'll do it as a 5, right? So we know obviously 15 times 15 is 225. So then maybe you would try 25 times 25, but that's 625. So it's still not enough. And then if you went up to 45, you'd eventually have gotten it. Okay, what about 57,600? Wow, that's a big number. So what we're going to do in this unit was we're going to learn different strategies for breaking things like this down. But obviously, you know it's going to be more than 45, right? And granted, you can use a calculator and just figure it out, but it's actually 240. Okay, for 6, hopefully you got 6. 7, you should know that one is 20. This one is obviously 2. And what about this one? Hopefully you had 60, right? Because 6 times 6 is 36. And then just if we add 2 zeros or plus 1 0 to the 6, then we're good to go. Okay, so our learning target here is you're going to learn how to work fluidly with radicals. Okay, and once again, I will be your partner. For each operation with square roots, compare the results obtained using the 2 indicated orders of operations. What can you conclude? Okay, so one key in remembering when you do this is remember that a radical sign is a grouping symbol. So for example, where we have the square root of 36 plus 64, you would do the 36 plus 64 first and combine those together to be 100 and then take the square root of those. So what do you think? Think this one's going to work? Well, what's the square root of 36? It's 6, right? And the square root of 64 is 8. So that equals what? 14. Does that equal the square root of 36 plus 64 all under one radical? Where 36 plus 64 is 100? No, because the square root of 100 is 10, right? So the answer is no. Okay, so what do you think in general, right? Remember, if you come up with one, what we call counterexample that you'll see on the next slide, you can't say that something is always true, right? So in general, do you think this is true? And the answer is no, because that example was not true. Okay, well, what about with multiplication? So again, let's try this. So what's the square root of 4? 2. What's the square root of 9? 3. So we have 2 times 3 or 6 on that left side. And then what about 4 times 9? Well, that's 36. What's the square root of 36? 6. So yes, it works. So when it's multiplication, can we multiply, combine? Will it work? Yeah. Or in other words, could we go from this right here, the square root of AB, and split it? And the answer to that is yes, you can. Okay. So, and we also learned here that AB to the 1/2 power is the same as A to the 1/2 power, 0.5 power times B to the 1/2 point power, the 0.5 power, which is that. Remember we learned that with the exponents, that if it's exponent, you got the T-Rex arms and it just grabs a parentheses, so everything gets raised to that power. Okay, what about subtraction? Go ahead and do it. Tell me whether it works. The answer is no, because 8 minus 6 is 2. I know the square root of 28 is not 2. It's somewhere between 5 and 6, isn't it? So in general, is this the same equivalent to that? No, it's not. So we couldn't take the square root of A minus B and make it the square root of A minus the square root of B if we wanted to. Okay, what about with the division? Try it. So did this work out? The answer is yes, it does. 10 is the square root of 100. 2 is the square root of 4. Is that the same as the square root of 100 divided by 4, which is 25? Yeah, it's equal to 5. So the answer is yes. So in division, we can split. Okay, we can split. And we previously learned that, right? We know that the square root of A over B is the same thing as the square root of, or is the same thing as the quantity AB to the 1/2 power. We can split those. We've seen all this. Okay? That's what's kind of nice about doing this in 9.1. We used to do this lesson actually right after 6.2, because that was where we learned about exponents, but it's kind of nice to come back to it now. All right, so again, counterexample is an example that proves that a general statement is not true, right? Because if it's not true for everything, then it can't be a general statement, okay? For each general statement in exploration one that is not true, write a counterexample different from the example given. In other words, they wanted you to write something like this that does not work. Okay, so go ahead and try doing one for subtraction and one for addition. And then here's a couple samples that I did. Because the square root of 13 is about 3.61. That's not equal to 2 plus 3. And then here's a subtraction one. Okay. All right. So let's jump into and take a look at something different. When we simplify radical expressions, and a radical expression is an expression that contains a radical. Okay, that's obvious. Just like a variable expression is an expression that contains at least one variable. Okay, so radical expressions. An expression involving a radical with index n is in simplest form when these three conditions are met. Okay, and by the way, remember the index, what that is? That's the root index. Remember, like it's a square root or a cube root or a fourth root and so forth. So what we're talking about is simple rad form. Okay, so when we're simplifying radical expressions, we have to make sure these three conditions that are listed here with the bullet points are satisfied. Okay, the first one is that you cannot have radicands, no radicands with perfect nth powers as factors other than 1. So in other words, you can't leave something as the square root of 4, right? Because you could simplify that. Oftentimes we call that no perfect square factors in the radicand. So let's see, what would be another example? You can't leave the square root of 12, because square root of 12 has a perfect square factor of 4 in it, okay? So you would have to break that down from square root of 12 to square root of 4 times 3, and then the square root of 4 is 2. So you would get 2 times the square root of 3. Okay? Another example with something other than just a square root would be like, you can't leave something like the cube root of 8, right? Because the cube root of 8 is 2, right? Because 2 times 2 times 2 is 8. So you'd have to simplify that. It's not fully simplified if you leave it like that. So that's the first condition. No perfect square factors in the radicand. Second one is that no radicands contain fractions. Okay, so you can't have any fractions involved here that are under a radicand. Okay, and then you can't have radicals in the denominator. No rads in the denominator. And we're going to learn how we take care of simplifying an expression that has a radical in the denominator. We'll learn about that. But these are the 3 rules that you need to know. Okay. All right. So let's get into some of these rules here. Okay. The product property of square roots basically says what we learned in the exploration a little while ago, that the square root of a product equals the product of the square roots of the factors. So if we have the square root of 9 times 5, you can split that. And then we could take the square root of 9, right? Because there is a perfect square factor in 9. In fact, it's 9. So that becomes 3 root 5. Okay. Or in algebra, using variables, if we have the square root of AB, then you can make that the square root of A times the square root of B. Okay. Now, what you're going to see when we get down into these problems is there's different ways to do this. So if you look at the study tip on the right, where it says there can be more than one way to factor a radicand. An efficient method, probably the most efficient method, is to find the greatest perfect square factor. Okay. So if you look at the square, what does that mean? Well, if you look at the square root of 108 in example A here, you might say, oh, well, I know 4 goes into that because 4 goes into 8, right? That's the divisibility test for 4 is go into the number that makes up the last 2 digits, right? So you might split it up that way, but that wouldn't be the most efficient way to do it. The most efficient is to factor out the greatest perfect square factors. Remember those perfect square factors? What are those? 4, 9, 16, 25, 36, 49, 64, etc. So you could rewrite 108 as 36 times 3, and then you can split it using this property up here, and then we can take the square root of 36 and get 6 times the square root of 3. Now, some people might say, well, couldn't I write it as the square root of 3 and then a 6 after it? If you do that, it's going to look like the square root of 36. So generally, what we call outies, because they're not under radical signs, go in front of the radical, just so we avoid that problem. Okay, then look at B here. Here we're taking the square root of 9x to the 3rd power, okay? So again, factored using the greatest perfect square factor. And then we have another study tip here that's important. So in this course, whenever a variable appears in the radicand, assume that it has only non-negative values. So it's a little complicated, but just in other words, don't worry about if x is a negative at this particular time, okay? So again, and we did this back in chapter 6 a bit. We could break this up to, because we can't take the square root of x to the 3rd, but we can take the square root of x to the 2nd, it's x, right? So if we split the x to the 3rd up to x to the 2nd times x, and then split all the 1 radical into 3 of them, give them each their own, because it's multiplication and we can do that. Why? Because we saw that that worked. Remember, we saw that that worked over here. So we can take the square root of 9, which is 3. We can take the square root of x squared, which is x. So those are our outies. And then can we take the square root of x? No. So we just leave it. Okay, so let's try some of these. Square root of 24. Is that one of the perfect square numbers? No. But does it have a perfect square factor in it? Does 4, 9, 16 go into it? Yes, 4 does, right? So what we want to do is we could split this up to 4 times 6, okay? And if I split it into the square root of 4 times 6, then I can split that into the square root of 4 times the square root of 6. And then I can take the square root of 4, which is 2. So I get 2 root 6. Okay. Now notice this negative sign's on the outside of the square root, right? So we're just dealing with the square root of 80 here. Okay. So what's one way of doing this? Well, the best way would be to look for the biggest perfect square factor that goes into 80. And you may not recognize them, and that's okay, but 16 actually goes in. So you might write it like that first. And then again, what's the square root of 16? You can split it, sorry. And then you can take the square root of 16, which is 4. Remember, this negative is just kind of sitting there waiting to be slapped on at the end. So it's negative 4 root 5. Okay. Okay, then a couple of variables here. We can split this. Can we take the square root of x to the 3rd? No. But if we take it and change it to x squared times x to the 1st, then we can take the square root of x squared, can't we? So what do we end up getting? Square root of 49, which is, right, 7. And what's the square root of x squared? X. And then we can't take the square root of x, so we just leave that like that. Okay, try the last one. What do you think you're going to have to change that end of the 5th to? And what perfect square factor goes into 75? So how would you split that up? Hopefully you said 25 times 3 for the 75. And end of the 5th, you would just change to end of the 4th times end of the 1st. And so the square root of 25 is an outie of 5. The square root of end of the 4th is an outie of n squared. And then what's left? A 3 and an n. Okay. All right, onward. So let's practice quotients now, right? Because we saw that with quotients, if we have a radical of a quotient, a fraction, we can split it, right? Okay. So here we go. Let's do that. So square root of 15 over 64. Well, you can split it. And then can you take the square root of 15? No, right? Can you take the square root of 64? Yeah, and it's 8. Have we satisfied all three conditions of simple rad form. Let's go back and look. Under simple rad form, no radicals have perfect square factors in the radicand. Square root of 15 doesn't, so we're okay with that. 4 doesn't go into it, 9 doesn't go into it, 16 doesn't go into it. Do we have a radicand with a fraction? No, we fixed that, right, by splitting it and then taking the square root bottom. So that, no, it's not in the radical. And are there any rads in the denominator? Do we have a radical in the denominator here? No. So that works, simple rad form. Okay, so what about the square root of 81 over x squared? Well, you could split it, right? And can we take the square root of 81? Yeah, it's a perfect square number, 9. And the square root of x squared we know is x. And we're good to go if we comply with all the simplest form rules. Okay. So you might be saying, well, gosh, what if it wasn't just like a square root of 64 in the denominator that made a nice 8, or the square root of x squared, which made an x? What are we going to do? Well, we're going to learn that in this lesson, in this half of the lesson. We'll be getting there shortly, but let's do a few more examples here. Okay, so here, notice what's the first thing you notice that's different about this problem? Okay, hopefully you said that it's a cube root, right? So we're looking for cube roots. So remember what the perfect cube numbers are, right? It's the first one besides 1, obviously, because 1 times 1 times 1 is 1. 2 times 2 times 2, right? Which is 8, right? Or negative 2 times negative 2 times negative 2, which is negative 8. And then what's 3 cubed? 3 or negative 3 cubed, right? It's 27, right? Or negative 27. 4, 64, or negative 64. 5 is 125 or negative 125. 6 is 216 or negative 216. 7 is 343 or negative 343. And after that, you probably just don't really need to worry about ones bigger than that at this point. Okay, so we know negative 128 is not one of those numbers, but what's the biggest perfect cube factor that does go in? Yeah, it's negative 64 times 2, right? Then we can split it. We can take the cube root of negative 64. It's negative 4. Can we take the cube root of 2? No. So we just leave it how it is. We're not going to approximate it by figuring out what that is approximately on the calculator. This is the perfect answer. It's fully complete. Okay, so now what about the cube root of 125x to the 7th? Well, fortunately, we know 5 cubed is 125. So that's going to be really easy to do. But is there a cube root of x to the 7th? No, we would need to find it where the exponent is, or the exponent on the variable is a multiple of 3, right? So what's the first multiple below 7? That's a multiple of 3, 6. So we change it to x to the 6 times x. Then we can do the old splitteroonie thing here, right? Quotient property of square roots. Square root of, or cube root, excuse me, cube root of 125 is 5. Cube root of x to the 6 is x squared. Remember, x is x squared times x squared times x squared. We add the exponents, right? So that would be, that one is x squared. And can we take the cube root of x to the first? No. So we can just leave it like that. All right. Here's some more examples. Here we want to split this, right? Can't take the cube root of just y to the first, but we can take the cube root of 216. It's 6, okay? On this one, split it, okay? 8 and 27 are both perfect cube numbers, so we're gonna be able to work with those. X to the 4th, we can't do completely, but we can make it x to the 3rd times x, and then take the cube root of x to the 3rd. And y to the 3rd, we can do it as we can take it. So check out what we have here. Cube root of 8 becomes the 2. Cube root of x cubed is x, because x times x times x will get you back to x to the 3rd. Can't do the cube root of x to the 1st. So that's our numerator. And the denominator, cube root of 27 is 3. Cube root of y to the 3rd is just y. Simple rad form, right? No perfect square factors or cubic factors in the radicand right there. No fractions inside of radicals, under radicals, and no radicals in the denominator. So we're good to go. All right, so why don't you try some of these and see how it goes. So on the first one, you'd want to split it, right? By the way, if this had been like a 24 over 9, you could reduce that fraction inside if you wanted. I'm not saying that that would necessarily be the best way to do this problem, but you can do that. You can, it's a grouping symbol. You could simplify it inside if you want to. Okay, so if we split it like that, we get the square root of 23 over the square root of 9. Is there any perfect square factor in 23? No. So we can leave that as is, and square root of 9 is obviously 3. Okay. All right, try this next one here. So you're going to split that, right? And then square root of 100 is 10. Can you do anything with square root of 17? No, and we just put the negative sign. Okay, try the next one. Hopefully you split it and you realize you can take the square root of both. Excuse me, and you get 6 over z. All right, how about this far one on the right? Okay, you can split it, right? And then even split the 4 and the x squared, right? Square root of 4 is 2, square root of x squared is x, and the square root of 64 is 8. Are we finished? Is this fully simplified? No, 2 and 8 can be reduced to 1/4, so we get just 1x or x over 4. Again, if I wanted to, I could reduce the 4 and the 64 inside the radical, and then I would have made this a 1 and a 16. I still would have ended up getting a 4 down below. So either way works. Doesn't matter. It's whatever you prefer to do. Okay, how about the cube root of 54? Is it 54 a perfect cube number? Is it 8, 27? No, but 27 goes into 54 2 times, right? So if you wanted to, you could change the 54 to cube root of 27 times 2 and then split it. That's cube root of 27, 3, and we can't do anything with cube root of 2. So oops. So we okay, this next one, cube root of 16x to the 4th. Is there any perfect cube number factor that goes into 16? Yeah, 8, right? So what we could do is change the 16 to an 8 times 2, the x to the 4th to x cubed times x to the 1st, so we don't put the first on there, right? And what can we take, what cube roots can we take for these 4? Can we take the cube root of 8? No. It's 2. Can we take the cube root of 2? No. Can we take the cube root of x cubed? Yeah, x, right? Because x times x times x will get us back to x cubed. So that's an x. And then can we take the cube root of x to the 1st? No. So what's left under the radical? Cube root of 2x. Okay. All right, how about this next one here? Okay, hopefully you're seeing you want to split it. And then we can't take the cube root of a to the 1st, but can we take the cube root of negative 27? I know you're thinking, well, it's a negative. How can we do that? Well, it's cubed. Is there a negative times a negative times a negative? It'll get us a negative. Yeah, negative 3. And then I just moved the negative sign up to the middle. You could do that, or you could just leave it. Okay, then try this last one here. See what you think you can do. You decided to split it to start. And can I take the cube root of 25? No. What can I do? Can I take the cube root of c to the 6th, though? Notice how I split up c to the 7th to c to the 6th times c to the 1st. Yeah, c squared times c squared times c squared will get you c to the 6th, right? And then I'd have a c, and d, the cube root of d to the 3rd is just d to the 1st. So we have that. And then can I take the cube root of 64? Yeah, it's 4. So hopefully you're seeing why it's so important to know these perfect cube numbers and perfect square numbers. Really helpful when you have something like this. You can just do it like really quickly. Okay. Now, on all of these problems, what always happened in the denominator after we split it? You never had a radical, right? So you're probably thinking, okay, well, now what do we do if we do get a radical? And what we need to do is what we call rationalizing the denominator. And the reason we call it rationalizing is that we have rational and irrational numbers, as you probably remember. An irrational number involves a square root in it. Also could be something like pi, because there is no, to be a rational number, you have to be able to be written as a fraction that either has a terminating decimal, like 3/4, like 0.75, and the story, or that repeats in a pattern, like 1/3 is 0.3333 forever, right? And with square roots and with pi, we don't have a pattern like that, and they go on seemingly forever. Okay, so if you look at this study tip, it says rationalizing the denominator works because you multiply the numerator and denominator by the same non-zero number, it could be a or whatever it is, which is the same as multiplying by a over a or 1, right? If you multiply a fraction by the top and bottom by the same thing, won't it still be an equivalent fraction? Think about it. If you had 2/4 and you multiply both the top and bottom by 3, you're going to end up with 6/12. Is 6/12 equal to 2/4? Yeah, it sure is. Okay, so watch what we do here. Okay, so we're going to first simplify it as much as we can. Okay, so gosh, there's nothing we can really take the square root of. Can't take the square root of 5. Can't take the square root of 3n. So what do we want to do? I mean, that would be fully simplified if we didn't have this rule where you can't have radicals in the denominator. Well, what you can do is multiply by the denominator, by the square root of 3n, as long as you also do it to the numerator. Because remember, what's square root of 3n over square root of 3n? It's equal to 1. Even though we don't know what n is, we know that a number divided by itself is equal to 1. So when we multiply in any times in any, we can rewrite it as square root of 5 times 3, which is 15n, right? That's in simple rad form. There's nothing that we can take the square root of that's there. And then a couple ways you can go about this. You can say that the square root of a number times itself is equal to what's under the radical sign. Or you could multiply and go 3 times 3 is 9, n times n is n squared, and then take the square root of all that, which gets you 3n. But just remember, if you multiply a radical by itself, you're going to end up getting what the radicand is, the number under the radical sign. See how I multiplied square root of 3n times square root of 3n, and I'm getting 3n there. So a couple ways you can think about it. Okay, and then in B here, there's nothing we can do with the 2. That's simplified. And unfortunately, we can't take the cube root of 9. But if we multiply it not by itself here, but get it to where, because it's cube roots, right? Get it to one of our perfect cube numbers under the radical, then we're in business. So what would we not need to multiply the 9 by to get us to a perfect cube number? Well, 9 times 3 gets us to 27, right? So if I multiply both top and bottom by the cube root of 3, then in the denominator, I'd have the cube root of 27, okay? On top, I'd have an outie 2 times root 3, the cube root of 3, which you can't really do anything with. You can just leave it like that. But the denominator, now we can take the cube root of 27, which is 3. You always want to look to see if you can reduce these outies, right? But it's a 2 and a 3. So in this case, we can. All right. And we're going to get to the rest of that in a bit. I do want to skip that page and get to this page. And let's do these. So you had to kind of look forward in your notes a little bit. And we'll get to what we're skipping here is when the radical in the denominator is, or when there's 2 terms in the denominator. And we'll get to that in the next lesson video. So we'll just do some of these. So we're going to do the top 4 here and this one as well, the yellow one. Okay, so let's see. Can we take the square root of 1? Or can we do anything with 1? No, it's just 1, right? Can we take the square root of 5? No. Okay, but we have a radical in the denominator. So what are we going to need to multiply the top and bottom by? It's got to be by the same thing, right? Because we're not trying to change the value. We're trying to change the way it looks. Okay, hopefully you said the square root of 5. And the reason, again, is that if we need to get rid of the radical, so we multiply it by itself. What's the square root of 5 times the square root of 5? It's equal to 5. Or another way to think of it is it's equal to the square root of 25, which is 5. Up top, we have 1 times root 5. But that's okay. We can just have square root of 5. let's go back. Oh, there we go. But 1 times the square root of 5 is just square root of 5, but that's okay. We can have that. It's in the numerator. It's just that we can't have it in the denominator. Okay, so what are you going to need to do on this next one? What would you need to multiply top and bottom by? Hopefully you said the square root of 3. And then up top, you're going to get the square root of 10 times 3, right? Which is the square root of 30. Is there a perfect square factor in 30? No. And then square root of 3 times square root of 3 is going to be 3. Voila, no more fraction in the denominator. Okay, and this one, what are you going to multiply top and bottom by? I hope you said the square root of 2x. Your numerator will be, remember it's in outie and innie, so we're not going to make this square root of 14x. It's going to be 7 square root of 2x. And then the denominator, right, 2x. Can I reduce 7 and 2? No. Can I reduce this 2x and this square root of 2x? No. One's in innie, under a radical sign, one's in outie. Not that. Okay, what about this, this next problem? Anything we can do to simplify first? Anything we can take the square root of? Yeah, y squared, right? We can do that. So take the square root of y squared, which is y, and we still have root 2, and then I split it and put it over root 3. What would we need to multiply top and bottom by? It said root 3. So what's root 2 times root 3? It's root 6. So we have y root 6. Again, outies can't be multiplied with any, so you can put them next to each other like they're being multiplied, but you can't actually multiply. And square root of 3 times square root of 3 is 3. Again, can't reduce the 6 and the 3. One's an innie, one's an outie. All right, cool. And then now let's try one of the cube root ones. Okay, so obviously can't do anything with 5. Can we, is there any perfect cube number that's in 32? And the answer is yes, there is, right? What is it? 8. Now there's also another way of doing this problem. So let's see if that's how I did this one. I did. Okay, so I reduced it down. Okay, so, and it's probably the best way to go in general. I'll talk about another way you could have done this too. What's the cube root of 8? Right, 2. So we have 5 over 2 and then cube root of 4. Then we have to think about, okay, well, I can't take the cube root of 4, but what if I multiplied it by the cube root of 2? Then I would get the cube root of 8, right? And what's the cube root of 8? 2. So I would have 5 times the cube root of 2 in the numerator. And the denominator, remember, cube root of 8 is 2 times this 2 gives us 2 times 2, which is a 4. Okay. Now, another way you could have done this is you might have just said, oh, you know what? I'm just going to go, I know 60, the cube root of 64 I can take. That's 4, because 4 times 4 times 4 is 64. So I'm just going to multiply top and bottom by the cube root of 2. So like you could have done this up there. So let me actually do that. You could have done this, right? You could have multiplied there. And if you had done that, you would have had 5 cube root of 2. These would have multiplied to give you cube root of 64, which would have ended up getting you 4. So a couple different ways you could have done that. Okay, well, again, we'll skip this and do that in the second video. Let's take a look at this word problem, because this one we can do. Okay, the distance d in miles. Oh, it's Miss Dickinson. How about that? Oh my gosh, in the lighthouse. The distance d in miles that you can see to the horizon with your eye level h feet above the water is given by the formula d equals the square root of 3h over 2. Don't worry, don't have to memorize this. It's just part of the word problem. How far can you see when your eye level is 5 feet above the water? Okay, so what's the 5 going to be telling us? Is that h or is that d? Yeah, it's h. Okay, so we would plug in for that, right? And then we need to simplify it. Okay, so 3 times 5 is 15. So we could have the square root of 15 over the square root of 2. Can we do anything? I think either of those numbers have perfect square factors in them. 4, 9, 16 is too much, obviously, right? So no. So then the question is, well, what do we need to do to get rid of that radical in the denominator? And hopefully you said, well, I'll rationalize it by multiplying top and bottom by the square root of 2. In which case I get the square root of 30 over square root of 2 times square root of 2 is 2. Now this is a word problem, so you probably want to go to your calculator at this point, figure out what the square root of 30 is, and then divide it by 2, and that comes out to about 2.74 miles. Okay. All right, awesome. So that means basically when you're down kind of at the ocean like that, and you're looking out about that many miles. All right. And let's see, I think the rest of the word problems we'll hold off on for right now. We can do this one as review in the next lesson. So that will be the end of this video, and you'll watch the second part of the 9.1 video series at another time. See you later.